everything.
Yeah, then also hi to everybody joining on YouTube. If you want to interact or ask questions at the end, of course, don't forget to join the Zoom talk as well, or try to prefer to join the Zoom talk over the YouTube channel. We are still waiting a bit for people to join, and we'll start. We start soon.
And in the meantime, just a bit advertisement. So the topic today is quite closely linked with the general theme of MLSLP conference. So it's a workshop. It's going to be a one-day workshop that will take place the day after InterSpeech. So on the seminar web page, you can find the link to the MLSLP workshop, and we have a selection of really great speakers. So I strongly advise you to submit a 2-page extended abstract or a 4-page regular submission. It's a great opportunity to talk with people that are interested in self-supervised representation learning in particular.
So when is the deadline for that?
Submission, I think, let me just check. I think it's probably next week. June 10.
Okay.
So that's for the that basically for the paper abstract. So you can submit either, and then August 10th there will be the final abstract paper deadline. So you can submit something relatively short by June 10, and then basically submit the full version by August 10.
Well, thanks for letting me know. So maybe there's a good chance to submit something as well.
Absolutely.
So did you co-host that workshop at previous InterSpeeches as well? I think I remember joining something similar in India.
Yes, so there was one in Hyderabad.
There was
I remember
before, that one.
I think in San Francisco as well, and it's collocated with either one of the speech conferences or one of the machine learning conferences. But because now there is more transition from machine learning to speech, so we kind of, well, the other way around. So we're actually trying to organize a little bit more within speech community.
Yeah, the one that was co-hosted in Hyderabad was really great. So I really enjoyed that. Really good opportunity to get to talk to the speakers as well, of course, and really great invited speakers. So I'm looking forward to that. And we'll probably also join even if I don't submit anything.
Yeah, it's registration is not going to be registration is going to be free of charge. So it's a great event to attend. There will be a lot of interesting talks there. Right, I think it's 5:06. I think I've taken quite a lot of time, and welcome everyone to the next seminar. Today we will hear from Benjamin Milde talking about self-supervised representation learning and speech processing. Benjamin is almost done with his PhD at the University of Hamburg, and before that he completed his MSc and BSc at the Technical University of Darmstadt, where he early on started working on the subject of unsupervised unit discovery and elements related to the current topic that he will be discussing today. The floor, Benjamin.
Thank you for the introduction, Anton. So the talk today will be mainly about two models, one called Unspeech and the other called Sparsity. They each target different representations that are completely trained on untranscribed speech data. And at a couple of points, I will make pointers to work before that, even to something I did in my master's thesis, and then also to current work that was recently published by other groups as well. So the motivation for unsupervised learning, in supervised machine learning, we have labels for data points x. So we typically model some quantity like p, where y is dependent on x. And in unsupervised learning, we are concerned with training scenarios where no labels are present. So we typically try to model p of x. Its latent structure, we try to discover patterns in p of x or its distribution, and generally try to find interesting properties of p of x. So in clustering is, of course, one of the most well-known techniques for that. The thing is just that the lines between supervised and unsupervised learning can sometimes be blurry. So it is possible to reformulate this P of X problem as a supervised task by simply decomposing that into the dependency on, for example, previous data points, especially useful if there is some sense of structure, time-based structure. That you, for example, have in language. So this is how you would, for example, also train a language model. But you're using supervised learning techniques to essentially model something that has no labels, because you construct the labels kind of artificially. No matter how we define unsupervised learning, what we really want to take advantage of course, is that labeled data is scarce, and it's much easier to collect large quantities of unlabeled data. And especially in speech, that, of course, is much easier than having data transcribed. Now, I really like this term self-supervised learning that's gaining use in the last 2 years. So it's considered to be a form of unsupervised learning. And you really make clear that you're actually using supervision, but that the labels are kind of automatically generated usually. And they come from an artificial task that you define. And in most cases, you're not really interested in the performance of the model on that artificial task, but you are interested in the representations that, for example, a neural network would come up with to solve this artificial task. So in language, something you can do with self-supervised learning is, because language has this time-based structure and the ordering is important, you could try to predict a future data point, for example. And you could try to predict the present using the future or past. You could try to randomly omit certain parts of your sequence and try to predict that. Or just have one data point and try to predict everything else. This sort of learning scheme is very successful in NLP. So when you have text data that is categorical. And for example, this first task would then be
recording in progress.
Language would be a language model, for example, LSTM or GPT. The second and the last one would be word2vec, different modes of doing word2vec. So that is essentially very useful for getting a semantic representation of words in NLP. And then, and this is kind of gaining popularity recently, you would have these masked language models, for example, BERT. They are now virtually in every supervised task in NLP, people would use a pre-trained masked language model, such as BERT, and then use transfer learning to their supervised tasks. When we try to transfer that to audio, it is essentially not as easy as it is in text. So when we are creating this artificial task for text in NLP problems, for example, let's predict the next data point. Let's predict a future word in a sequence. We could simply use any multi-class prediction model to do that. And then just one word in the vocabulary would be one of the classes. And that actually, even though it's very simple, works amazingly well. It's not as straightforward in speech, because of course, speech is continuous. And many years ago, when I started my PhD, I very naively tried to implement sort of this prediction task where I would have an audio sequence and then I would try to predict the next block very naively. For example, with an LSTM, I would try to predict this whole block at once. And it just did not work. So it was terrible. generative model. It would just produce noise. And the representation it learned weren't useful at all as well. So now in 2021, there are several ways of doing exactly that. They all involve certain tricks to make it work. For example, vector quantization, and then it's very similar to text again because you have categorical data. There's new machine learning techniques like general adversarial training to make this work. But by and large, my point still stands. It is much more difficult to apply these things to speech than it is working with text. The inspiration for Unspeech actually came out of Word2Vec. And in Word2Vec skipgram, you would not directly try to predict context word from a target word. So you would reformulate this problem actually into a binary task and have pairs such as suit and dark or suit and greasy. And the artificial task would be, is suit and greasy a context pair? And then you would negatively sample from the vocabulary. So you would use suit and then, for example, cat, just any word from the vocabulary. Or is that some artificially sampled pair? And since that is actually binary, and you could use any machine learning model to output this binary classification, it also works well with speech. So similarly to what we've seen here in text, we would have a target and then the context of that target. And we could also say, well, is this window and that one window a context pair, or is it just something that is randomly sampled? Then this is from 2018. So we used convolutional neural networks here. These are these yellow boxes. And we would embed these windows into these blue vectors here, have a dot product between two of these, and then we simply have logistic regression on top of that, logistic loss and a binary classification. In 2021, you would probably use transformers for these yellow boxes, but that's actually not so important. More importantly, you embed this into a fixed size vector here. So what happens if you do that? So we are not interested in the artificial task. We are interested in these embeddings, so we can actually throw out everything else. So what happens if you do that? Something else happens. So not the same as we've seen in NLP. You basically get a very similar vector for a whole sequence. So of course, sequences can be longer than these windows that we're trying to embed. And we can simply use a window approach and go for the whole sequence bit by bit. And then we would get this representation here for an unspeech embedding of 100. So n is 100. It is similar because it is actually modeling speaker properties. So if we would take the average of every utterance, and this is trained on TED Talks here, and look into from which TED Talk is that coming from, it would start to cluster speakers. So sometimes you have TED Talks with more than one speaker as well, of course. And why does that happen? Well, because if we sample these consecutive windows, they have a high probability to come from the same speaker. And if we randomly sample these windows of speech, they have a high probability of being from different speakers. So solving that artificial task basically means to model speaker properties. This has been known actually for a long time, and it's been called the stationary hypothesis in speech. So for example, there's an old paper from Jin et al. In 1997 called Automatic Speaker Clustering. And he says our algorithm takes the advantage that consecutive segments are more likely to come from the same speaker. In practice, we regard speaker as a generic concept, which really means speaker with channel and background condition. Now, the same thing actually happens in Unspeech as well, that we not only model speaker properties, but also channel and background properties as well. And in our work, we call this generic concept then a context. So the context of an utterance would be what Jin called this speaker with channel and background condition. We evaluated on in many different settings. So as a speaker embedding and comparing that to other speaker embeddings, to mostly supervised speaker embeddings. In context clustering, then in automatic speech recognition evaluations with Caldi, and then also downstream tasks. So if we compare Unspeech to iVectors, which would be one of the most well-known speaker embeddings, we see that we sort of model speaker properties, but of course a supervised iVector would be much better than Unspeech. So here, this error rate is called the equal error rate. That's often being used in the same different speaker experiments. And low is, of course, better. But this confirms that we're learning a lot about speaker properties in these embeddings. Now, in context clustering, we use HDBScan, which is a modern density-based algorithm. So it's nice that basically out of the box, it produces very good results without tuning. And it automatically selects n, so you don't have to define how many clusters you want to have. It's also nice that it scales very well to very large quantities, because the average case complexity is just n log n. So we used HDBScan on iVectors and on Unspeech vectors, and then tested the difference with normalized mutual information, the difference to basically a gold clustering where each utterance is coming from a TED Talk. So 1 would be the best score you can get here. And we basically confirmed something similar, that the supervised embeddings would more closely resemble that kind of gold clustering here, and that we are a bit behind, but still able to capture a large part of this gold clustering here. In another experiment, we used what is coming out of this context clustering in speech recognition. So in this experiment, we just use the IDs and then train the system normally with iVectors and bootstrapping, of course, bootstrapping of GMM, HMM models, and then TEDN and HMM models with Caldi. And if we would just assume a baseline where we say, okay, each utterance is its own speaker. So if you would have no speaker information at all with your corpus, you would use that to train the system. And between that, we see a 10% reduction of word rates in TEDN and HMMs. The gain is much larger for GMM, HMM systems. And we are just a tiny bit better than using the clustering that comes with the corpus here in this case. So this would actually only be useful if you don't have any kind of speaker annotation with your corpus, and then would train your speech recognition system on that. In another experiment, we replaced the iVectors with unspeech vectors. So here we would, similarly to the generic recipe, we would just append the context vectors to the input and then just train everything normally. And in this case, well, it's hard to say, but on the def set, for example, iVectors would be better on the, excuse me, we are comparing line 2 and 3 now. So actually, iVectors would be better on TED-Lium if you do that. And it is just slightly better than having no context vector at all. But you can do something else if you want to do adaptation to a new data set. So if you have a different domain, let's say a domain that has a lot of conversational speech, and you want to apply that to a different data set, then you're seeing gains. So this is actually the next experiment. We do everything as before and then test on out-of-domain test data. So in this experiment, the out-of-domain test data is coming from Common Voice, and we would actually train the unspeech embeddings on Common Voice, but would train the speech recognition system on Tetlium. And here we see a like I think 10% relative reduction of word error rates on the out-of-domain data. So so far, these embedded contexts are mostly about speaker characteristics and, of course, background and channel conditions as well. But what about other types of contexts, especially what about phonetic contexts? So the embedding can be influenced with negative sampling. Just by changing the negative sampling, we get different embeddings. So we can do a step 1 where we train the unspeech model as we did before. And then we use the IDs that come out of that clustering to sample negative windows only from the same context. So if we do that, we're not modeling speakers anymore. We're modeling basically everything that happens inside speakers and in clusters of these contexts. I mean, we still have this limitation because we use this convolutional network where there is a fixed size. And if we use the same fixed size we did before, which was 320 milliseconds, we basically have, if you would look at phones, that would be about 5 phones on average. And we start to see that similar sounds are kind of grouped together if we look at common 5 grams. So we look at the most common 5 grams in Tetlium, which happen to be these. So the most common phone 5 grams, which most often would also correspond to words or parts of words or to words, like in this case, this is. And then we would look at this through t-SNE, so dimension reduction to 2 dimensions of these unspeech vectors. And we would see that if we have the uniform unspeech embeddings, there is no clustering of these 5 grams happening at all. It's just the same speaker kind of embedding that we had before. And with this in-context negative sampling, we would start to see groupings of phonetically related 5 grams. I say start to see because some of these are still all over the place. But for example, here at the bottom of this figure, would have many different variations of and. So silence and silence and silence, S silence and. So there's like an S from a previous word as well. Thing and something that starts to group here. So we start to see more phonetic relatedness here. And this can also be quantified by using downstream tasks. So these are actually new experiments. So between now and 2018, when we published Unspeech, a lot of other models and networks used similar ideas for self-supervised learning of speech embeddings. One of the newest ones is called Trill. That is from, I think, 2020. And it's directly modeled in the time domain. So they don't use this representation layer, but we used FBank. You can also use MFCC with Unspeech. And there's much better machine learning, of course, than we did with the convolutional networks. But actually, Unspeech still gets competitive scores. So if we, for example, compare Trill and Unspeech on SAVI, which is an emotional classification task. So the task is to classify 7 different emotions. And this data set is very small. It's like 400 utterances. We would see that these regular unspeech embeddings would actually get fairly low accuracy. But with this negative sampling trick, we are able to nicely have a nice gain in accuracy here. And but it still seems to be the case that if we use a speaker-dependent setup, of course, we get much better scores. So in this experiment, we use a very simple classifier. We just use linear regression on top of these embeddings. And that confirms actually that there is something useful in those embeddings, and that that you can use them to very quickly model these tasks. And now we are still a bit behind the best score for speaker dependent here, for example. We have actually quite good scores for speaker independent SAV. We are also quite good with speech commands. Something interesting is actually that the top layer is actually not the best. Is not the best location to extract the embeddings. It is better to extract them a bit earlier. So in our case, that is right after the convolution layers, before the final layers. And that is very similar to all of these other embeddings. So one of the intermediate layers worked much better in these tasks than the last one. So Unspeech is available, source code is available, models can be downloaded as well on unspeech.net. So now on to something else. So I go back in time a bit. I go back to 2014. So that is briefly something that I did in my master thesis. And there I worked on acoustic unit discovery. So a very simple algorithm that you can use is blind segmentation. And in blind segmentation, you try to find good segmentation points for acoustic units in speech without any labels. So in this work, I didn't use any neural networks, not as popular as they are now. I simply used dimension reduction on MFCC vectors or similar. And then you would get this kind of representation. And I would look at two windows on this reduced signal and look for the points where the differences between these two windows is the biggest. So this is called blind segmentation. It's been done before that as well in 2006, 2009. And all of these works make use of spectral discontinuities to find these boundaries. And then in my work, I did a fixed sized embeddings that I defined by hand, so no neural networks again. So something really simple, like take the first vector of a sequence, take the last vector of a sequence, and then just take the different averages over different time spans of the whole sequence. And then just construct one super vector out of these parts. So this kind of very simple baseline actually works remarkably well. So this is a sequence from Timid, and in the second row, you would have the human labeled phone boundaries. And in the third row would be the predicted boundaries from the algorithm. And this line here are the differences over these two windows. And whenever we have these maxima, we would postulate a boundary at these places. If we have these fixed size embeddings, of course, we can use any clustering algorithm. And I made use of k-means as well here. So I would have to define n, of course, as well. And if you configure the parameters, then you can sort of come up with something that approaches phoneme-like units. So just to show you how that sounds, I will play a few examples. So unfortunately, I have to go out of the presentation here. So I would make this cluster audible by just concatenating different versions of these units, and you would hear something that is a repetition of the same unit, but taken out of a signal from different places. So that, for example, would be unit 13. Unit 14. So if you then would look for very common n-grams, you would start to hear words as well. So this was done on a German data set. So these are German words, of course, as well. So one of the most common 4-grams would be 18, 12, 5, 23, and it sounds like this.
6 Setz, Setz, Ruhe, Position, Setz, Sitz, Setz, 6 Setz, Sitz, 6 6 Sitz, Sicht, Sicht, Sicht,
I also play some of the others.
Sicht, 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 6 Setz, Setz, Ruhe, Position, Setz, Sitz, Setz, 6 Hisbollah, Hisbollah, Hisbollah.
Okay, let me stop here. Probably enough of those. Let's go back to the presentation. Okay, so this works nicely. There is a huge limitation, and one I probably didn't highlight as well in the master thesis. This only works on a single speaker corpus. So I have taken this data set from news, from German news, and it would typically be the same male speaker in these utterances. So there is no speaker independence at all. And it is difficult to apply the same thing over a data set with a diverse set of speakers. And if you would look at these windows, so basically if you have blind segmentation of speech and then independently look at these windows, that's how they would look like. So this could be a unit that should be clustered, and this over here should be a unit that should be clustered. Both are now F-bank representations, and you would take the first and the last vector, etc. But it's really difficult to say if these should be the same, basically, unit, or if they should be different ones. And it's much easier to decide that if you look at the context of these units. So if you look at these two utterances, one is uttered by a male speaker, one is uttered by a female speaker. There are large differences, but you also see similarities. And it is actually the same utterance, and it is the same unit coming out of that in this example. So this is actually the motivation for sparse speech. We want to decompose this utterance into a context vector part. So that's basically everything we are not interested in. And then a discretization of speech that we, for example, can learn through self-supervision. So this could be basically like units, discrete units, and we would omit some of those and try to predict those. And then we also have this context vector that hopefully captures a lot of this variability, speaker variability, background variability, and so on and so forth. So in acoustic unit discovery, since 2014, of course, a lot happened. And Lucas Ondell, in his first presentation, had a very nice overview over related work in this area. Just to briefly repeat, there are three major approaches here. So one of the first ones is this segmental approach, something I've used in 2014 as well. That's been around for a while. Then there are all these neural network approaches. For example, an interesting result is that if you just train autoencoders, like the plain standard autoencoders where you would downsample and then upsample the signal again, these do not seem to produce any useful representations that have better phoneme discriminability than MFCC. But recently, there are much better models that are neural network based and that have very good phoneme discriminability. For example, CPC, contrastive predictive coding, and vector quantized variational autoencoders, and recently also wave-to-vec, that we'll briefly talk about also at the end of the presentation. Then there are Bayesian non-parametric models. So these have been very successful in these ZeroSpeech challenges, especially the first ones, 2015 and 17. So these models have one advantage, that you don't have to set the number of units in advance. So it's because it's non-parametric. A huge disadvantage is that they don't scale so well to large data sets. So in these ZeroSpeech challenges in 2015 and 17, there was just little training data, and these worked really well on just a couple of hours of data. Now, the proposed sparse speech model is one neural network that takes into account this concept of separating something into a context vector and a discretized representation. So we would have typical input features, for example, FBank, MFCC, and PLP. So in all of my experiments, I used PLP. That was also the input representation to a lot of these entries into these challenges in 2015 and 17. And we would have an encoder, which could be stacked LSTMs, and a decoder, then a memory component that also does this discretization. And then we would omit at certain time steps randomly, we would omit this representation. And then the decoder would have to decode the original sequence by using the context vector and this discretized representation. The memory component is based on memory networks. So you have a key addressing network and a value memory. So the value memory stores embeddings, and the key addressing network basically addresses these embeddings. You want to have a module that is, of course, differentiable so that you can apply standard backpropagation to your whole model. And here we achieved that by having a softmax and a sparsity loss. So when we apply the softmax, it means that this vector here in the middle of the key addressing and value memory network always sums up to 1. And we can make use of that in the sparsity regularization by maximizing this, this green vector here. So if we maximize any of these elements, the closer they become to 1, the more they push all other values to 0. So this vector would begin to be a 1 hot encoded vector. This is actually related to L infinity regularization. So similarly to L2, if you would have L infinity, that would basically resolve to the maximum of your vector as well. So if you, of course, if you minimize, you would have to take 1 minus the maximum of these elements. Then, of course, you have a degenerate solution, and that would be place all inputs into a single memory component, and that would get you the perfect score on the sparsity loss, but would of course not be any useful representation. And to discourage that degenerate solution, we would then use a diversity constraint, and that's simply the KL over this vector and a uniform distribution. So we want these elements to be uniformly distributed. Of course, linguistically, phones would not be uniformly distributed, but it's close enough for this kind of unsupervised task. The training procedure is multi-step. So we would have these 4 steps, and they look, the first step looks like a regular autoencoder. So we have the blue building block here, which is the encoder, and the red one, which is the decoder. We would train that to just reconstruct the input sequences. And we'll do that for a while. And then we cluster basically what comes out of the encoder and put together the encoder and the memory component and train that to predict these clusters. And at the end, we train the full system end-to-end, combining all of these elements. And we would then continue training for a while. So we continue training with the pre-trained memory component. And of course, once we continue training, we also add this sparsity loss and diversity loss on top of the reconstruction loss. So how does it look like? At the top here is the input sequence, which is PLP, and then the reconstruction of that with the missing information. So there's 33% of these data points which are omitted, and it has to reconstruct. And here we compare at the bottom different sparsity weights. So if we add the sparsity loss to the loss function, we can of course also add a weight. And the higher it is, the more sparse these representations would be. And here, this yellow color is high activation, so close to 1, and violet would be 0. So if the sparsity is high enough, it works really well to discretize speech. But at some point, this falls apart, and if the weight is too small, we would get this degenerate solution where one of these elements is active over time, and some very dense information is stored in all the other components, which are very small numbers, which are close to 0. We evaluate this using ABX. So Lucas Ondell in his talk also we had a great discussion about ABX at the end of his talk. Just to briefly recap, ABX is an evaluation where we test if a stimulus A or B is closer to X. And what's been often used is the minimal pair ABX discriminability. In my work, I test 2 different forms of ABX. So I test word ABX and then also minimal pair ABX. In word ABX, we would have A and B, which are different words. For example, A is dog and B is cat. And then we will have X, in this example, also cat, but spoken by a different speaker. And the question is A or B closer to X? So this example, B is closer to X. But you want to really test if your representation captures some semantic aspects, or if it's simply just, again, using these speaker characteristics, which would get it the wrong pair here. In a triphone minimal pair task, we pose phonetically the most difficult task. So we have words that are just discriminated by one phone. And they are also difficult for non-native speakers. So for me, it's actually difficult to say bag and bag without this sounding exactly the same. And here it's just differentiated by one center phone. The nice thing about ABX is that it is representation agnostic. So it can be applied to sparse and dense representations as well. The representations don't have to have the same length. So it uses dynamic time warping to compute this distance over sequences with different length. Locally, at the frame level, we can actually define the distance function, and different distance functions are useful in different tasks. So cosine distance would be most suited for embeddings, for dense embeddings, and I'm using a lot of KL distance because that is useful for posteriors. And of course, if you have one hot vectors, you can also use them symbolically, and then you could simply test for equality. So since it's a representation agnostic, you can, of course, test ABX on MFCC and PLP as well, which got me fairly high error rates on this LibreSpeech task here. PLP DPGMM is one of its non-parametric models. So DPGMM, Dirichlet process Gaussian mixture model, trained with PLP as input. And that is actually a strong baseline on this task. So I did a parameter search. I tried different modes of initialization as well. So I tried DPGMM as well. K-means ++ is simply faster and better and scales better to larger input sizes as well. But we have to set n here, of course. So if we are setting n, we need to search also for values that work well. I also search for good sparsity and diversity values. So it turns out that moderate sparsity and higher diversity would work best. And as context vector, you can use, of course, unspeech embeddings. So what we talked about in the first part of this presentation, there's a simple alternative where you don't have to pre-compute another model. You can also take the average over all the encoder states and use that as a context vector. And that worked actually a bit better than explicit context vectors. Then, of course, you could also use I-vectors, etc. If you really want to make this context vector based on speakers. I tested on ZeroSpeech 2017 on the English test set, and of course lower is better here. There are different settings to test this. Usually it is more difficult to get good scores for smaller utterances. So 1 second, then there's also 10 seconds and something longer. 120 seconds. And we have these two different scenarios. So in one, this ABX task would be across speakers, and the other, it's AB and X would be coming from the same speaker. So let me break this down quickly. We got the best results with fairly small n, so n 16 to 20. And what comes out of sparse speech is better than MFCC, but it was not better than the best and winning entries of the 2017 ZeroSpeech challenge. So there's quite a difference actually between those. Now, this representation here is much larger than what comes out of sparse speech. So I think it's a few thousand. The elements are, the vectors are a few thousand elements large. So it would not be what you expect for a acoustic unit discovery. So you have lots and lots of units here in B. So if you are really interested in something that is symbolic, that represents your sequence symbolically, you can of course do a vector quantization. And if you do that on B, you actually get quite high scores because the dimensionality is so large. And if we do the vector quantization as well, which we should do, because we don't get exactly one hot vectors, but something that approaches one hot vectors. In this case, we get better scores on the vector quantized representation. So this is now really symbolic. And in the ABX distance function, we would really just use equality at the local level. In an updated version of sparse speech, I replaced the sparsity loss with categorical reparameterization. So this is actually a nice trick to have something discrete inside your neural network. So they are typically difficult to train with standard backpropagation. But in this reparameterization, you sample a noise vector G from the Gumbel distribution. You can also sample that from a uniform sampler by taking minus log of a uniform distribution between 0 and 1. And then you would simply add the noise vector with a weight to the logits of your softmax and divide that by a temperature parameter. So graphically, what happens here is that you have an input distribution from your logits, and you can draw different samples with different temperature from this input distribution. So as the temperature gets higher, we would approach a uniform distribution. And if it is getting close to 0, we would basically get something that is approaching one hot vectors. So the nice thing is that we can continuously basically sample between dense and sparse. So when we train these models, we can start with something dense, and at each training step, we make it a little bit more sparse until we end up at a very low temperature where we almost have discrete units. So this is exactly what we've been using. So instead of directly having this output of the encoder into the memory component, we would sample from the Gumbel softmax here and use these samples for the memory component. Since basically taking the averages of the encoder states worked better than explicit context vectors, in the updated model we just used that kind of construct and then use that as a context vector. How does the updated representation look like? So the nice thing is that we got better scores with higher n. So among the best performing models was N42, which is fairly similar to the number of phones in the English language. Depending on how you model it, can be 43 and 44, I think. And here, the nice thing about this improved model is that once we've trained it, we can output representations with varying degrees of sparse or denseness. They're just varying this temperature parameter. We can do that after the model has been trained. So this actually highlights a problem of ABX if you work with these sort of discrete representations. So even though that is nearly the same representation, we are getting a big difference between a bit more dense representations and the really nearly completely discrete representation here. Although it is nearly the same representation, just scaled differently here. So if you're using ABX with something discrete, you almost always are at a disadvantage if you compare your model to more dense and high bitrate representations. And I think that was also one of the results of the, I think, 2019 ZeroSpeech challenge, that if you compare different models on ABX, you have to take bit rates also into account. And Sparsity is producing representations with a very low bit rate. So we can produce basically symbolic representations as well. So the improved model, if you compare it to the old one, has an improvement of up to 30% on within speaker ABX rates, 22% across speakers. And we trained this now on a larger data set. So the model scales nicely to larger data sizes, 600 hours, and I also trained models on 6,000 hours of untranscribed English speech data coming from this new data set called LibreLite, which is, I think, an excellent data set for unsupervised learning in speech. The nice thing is that there are now no degenerate solutions, so training always worked actually. And again, 42 was the best N we seen in the ABX evaluation. And we also trained a simple one-layer LSTM phone recognizer on top of these nearly discrete representations with CTC. And that was actually better than PLP and MFCC, but the results are actually below CPC, contrastive predictive coding. So one of these other neural network-based self-supervised models that also produce much more high bitrate representations. So what comes out of CPC is, if you don't do any vector quantization, is basically just dense embeddings. So conclusions on future work. So the proposed model basically is able to learn quasi-symbolic representations of speech. And these representations are very compact and have better phoneme discriminability than MFCC or PLP vectors. I still think that DPGMM is a very strong baseline, especially if you train it on very small data sets. So as you take into account bigger data sets, these neural network methods start to really shine in the sense that they scale easily to larger data sets, while it is difficult to scale DPGMM to, say, 300 or even 100 hours. It takes a lot of training time. One thing that is fairly recent is that unsupervised ASR is becoming practical. So Bavesky published this a week ago, and that is the same author as in the Wave2Vec paper, and this is coming out of Facebook's group. And they show that they have nice results on completely unsupervised ASR, matching supervised ASR from 2 or 3 years ago in English. And they applied this to low resource languages as well. So in this scenario, you just have unlabeled speech and unlabeled text and train a full speech recognition system on top of that. There is a part in this training scheme where you generate these acoustic units. So that actually means that acoustic unit discovery is at the forefront of unsupervised ASR now. So it's an important ingredient and task in a full unsupervised ASR system now. How do they find this correlation between unlabeled text and unlabeled speech? Well, they use a generative adversarial network here that discriminates between real phonetic sequences that are coming out of your text. You take your text and build phonetic sequences out of that, and what's coming out of your discovered units. So with that, we are at the end of my talk. So I'm looking forward to a nice discussion, and I'm looking forward to your questions.
Perfect. Thanks, Benjamin, for a very interesting talk. Let's see if someone from an audience has a question. Please unmute yourself. Okay, and while we are waiting for people to... Oh,
hey, Benjamin.
Hi.
Thanks for a great talk. I need to run in 2 minutes, so I thought I'd sneak in a quick question. I guess the one thing about that last, the big unsupervised models, which is really impressive, is that they also rely on a huge amount of text resources, which they basically use to map that unlabeled text block in that slide here. And I was just wondering how important you think that is in terms of kind of giving the model an implicit language model in a weird way, if that makes sense.
So the question is, how important is having lots of text in this sort of setup here?
Yeah.
So this has been coming out recently. I'm still also looking at that. Since getting large amounts of text is even easier than getting large amount of speech data, I would say that it should be easily possible to get lots of text, and then that's just what you use. I don't know how, if it's still possible to train this if you just have a bit of training data here. What I know is that they are able to train this model, this sort of model, on low resource languages, and I would imagine that they have a much lower amount of text data simply because there isn't much text data, and it still works. So I hope that kind of answers your question.
I think you're right. I think there are some interesting cases where I don't know, if you're working with endangered languages, and maybe this is on the French, where languages might be unwritten and things like that, where the unlabeled speech approach is really attractive, or almost your only option, where you won't have that much text. But I agree with you that in general, if you're able to get speech in these quantities, you'll probably be able to get text as well.
Yeah, I would think so as well. Of course, for these endangered languages where you have no text at all, this wouldn't work, and you would want to have other models that just work on speech and just work on these sort of unsupervised units. I think this is really nice for all the languages which are in between, like in between low resource and high resource, if that works sufficiently well. Since probably also, I mean, GPU training computations are cheap, and manually labeling something is expensive. So I would imagine it's also cheaper to train these unsupervised models. And there surely has to be some sort of trade-off, that you need more unsupervised data than supervised data to get the same quality, or about the same quality. So of course, I was wondering if I can replace some of these steps with my models as well, of course. So I'm seeing that there is a lot of subsequent steps in here, and this Sparsity sort of wraps them up. So I'm hoping to still run these experiments as well and see if I can make some of my models useful in this framework as well.
Thanks for a cool talk.
And we have one very quick question from the chat. Are these embeddings task dependent? There is one question.
So we are talking about these unspeech embeddings, I would say.
Yeah, I imagine. Yeah.
So probably this slide is helpful for this question. So I'm actually still running these experiments, and as I said, this is basically taking my 2018 embeddings and I'm trying to solve these new tasks that others have solved in 2021. From this paper that the authors of Trill published, there are, I think, a few more tasks, and I would imagine that unspeech also works in these other tasks as well. They are a bit more involved because they also have combined modalities where you have speech and visual input as well, for example, which would be a bit more difficult for me to set up. But generally, I would say that between unspeech and this unspeech LC, these are totally different representations. So you would want to use unspeech in everything that has to do with speaker characteristics. And you would use unspeech LC probably in everything there, in any task where you want to have speaker independence. So emotion recognition, like this short command recognition here. So this is like 12 short commands, left, right, up, down, and so on and so forth. Since there is no context, it's also interesting to look at these as sort of a classification and not use a full ASR system. Then there would be other tasks like language identification, where I think this unspeech LC could work well as well. So I hope that answers the question.
Hopefully, we'll wait for the confirmation. In the meantime, let's check if there are more questions. Please go ahead and unmute yourself if you have a question. And while we're waiting, let me just ask you a very quick question. Given that you spent, given that you're doing your PhD in Germany and you spent quite a lot of time working on this topic, if you could go back now and return to the beginning of your PhD, what would be that direction in this area you would have actually started working?
So, I mean, one thing I would do if I go back to the beginning. So I started to work on basically self-supervised learning before this term was being used and before I was encountering this term in literature. And I started to do some interesting self-supervised learning, but I quickly abandoned some of these ideas. And I think I abandoned them too quickly. Because this sort of representation learning also yields useful results now. And if I maybe spent a bit more time trying to make it work, I would have found it a bit earlier than others. But I mean, I didn't. I abandoned this. Also, I worked on different projects. So I didn't work on unsupervised learning at all. In isolation, I looked at supervised learning as well, of course, and did a lot of ASR as well. Worked on German speech recognition quite intensively. So if I would go back with everything I've learned, I would do more self-supervised learning from the beginning, where it wasn't really known if that is actually a useful avenue to take. So I remember going to Interspeech, I think the first one in 2015, and I would introduce my topic and talk to others. And I would sometimes get very intense reactions, like this is a total waste of your time, like making unsupervised speech recognition work that doesn't work at all. You're wasting your time basically trying to pursue this. And there was just a fringe group of people that tried to do it. And then with the ZeroSpeech challenges, the whole field got bigger. And I would say now in 2021, where we see that actually we can even train full ASR systems unsupervised. This is like a fairly new insight. Knowing that it is possible would have helped in the beginning as well, where, I mean, everyone was unsure. Nobody was sure if that would work ever. Other than that, I think I would do the same things.
Yeah, I would go with that too. Right. Let's see if there is anyone else that would like to ask a question.
Hi, Benjamin.
Hi.
I myself, Gurnath. Thank you for the nice presentation.
Thank you.
I have a question. So does the accuracy on self-supervised task, if you get a very high accuracy on self-supervised task, that does means we will also get a very high accuracy on the downstream task.
Okay, it was a bit difficult to hear for me acoustically. Could you maybe repeat the question or
can I
talk a bit more loudly, maybe? Because it was very hard to hear acoustically.
Oh, sorry. Can you hear me now?
Yes, maybe I just amp up the volume on my speaker.
So I'm asking, like, you have a pseudo task, right? You're solving some pseudo task to get the embedding. If you get to like a very high accuracy on the pseudo task, let's say close to 100%. So does that mean does it mean that the downstream task will also get the very high accuracy?
Okay, I understood the question now. So is the artificial task accuracy somehow correlated with downstream tasks? Not necessarily, of course. It really depends on the downstream tasks. So if you would look at this and the downstream task would be speaker recognition, and this sort of artificial task is basically very similar to speaker recognition, then of course I would say there's a strong correlation. On other things, like especially when you want to have these speaker independent embeddings, I would say not necessarily so. So you could be overfitting on the artificial tasks, of course. And they could help and could not help. So there is no easy way to predict that other than trying out the downstream tasks in these cases.
Oh, yeah.
But so of course, if you have the like from random networks towards fully trained networks, there should be a difference.
Oh, yeah. So can we interpret these embeddings somehow, like is it possible to interpret like so these embeddings will correspond to these something like MFCCs or like spectrograms?
Sorry, again, I couldn't understand the question.
Sorry, is it possible to interpret these embeddings like after chopping off this classification layer, whatever the embeddings we get? Can we interpret it like somehow?
So if you chop it off, you're basically left with the hidden layer at this point here, and that becomes your embedding representation. So in the beginning, I was basically just assuming that whatever comes out of the top representation here would be best suited as the embedding layer. It just turns out, and that is possibly also downstream task dependent, that other layers inside this network might be better suited to your task. And again, there would be no simple way other than trying out these other layers as well. But from looking at the results of other similar networks, especially in this downstream evaluation, which I had here, all of these had better results on these downstream tasks. Here it is. If they take some intermediate layer. So that's what I've been doing as well. And I see also a slight increase of accuracy here in SAVI, for example, and a larger one in the speech command downstream task.
Thank you very much for answering my questions.
Ben, I think also one part of the question that Gurunath had was whether there is some form of interpretability in the embeddings that you extract. For example, similar to MFCC, where you have, for example, low frequencies at the bottom, then you have a high frequency at the top. Is there any kind of structure or something like that coming out of them? If you kind of plot, for example, them for one file, say.
Well, the structure is always going to be that in the embedded space, the distance between two different embeddings has some kind of meaning. But other than that, each time you retrain your model, your embedding transformation will look totally different. So whatever structure you discover in one of these embeddings, it will not be the same if you retrain the whole model. So I would say no, other than some kind of meaningful way to deal with distances in the embedding space, looking at individual elements in the vector or so would not be useful. Or it's difficult to find any structure there at that level. Essentially, it is a black box, and you don't know what comes out of it until you look into it and try it out on downstream tasks or looking at clusters and so on and so forth.
Thanks from Gurunath. Let's see if there are any more questions.
Recording stopped.
Oh, there is a question, or is that not a question from Zach?
Not a question, just saying, thank you.
Go ahead.
Not a question, just saying thank you.
Oh, got it, sorry.
Okay, thank you.
Right, if we have no more questions, I'd like to thank Benjamin for giving a really, really interesting talk. And I encourage everyone to submit the papers to MLSLP on June 10th. Perfect. Otherwise, thanks again for everyone for attending. And in 2 weeks, we're going to have another very interesting seminar. And please stay tuned for emails from Hao with the details regarding the next seminar. Thank you very much, everyone, and goodbye.